Hopefully we can wrap up our study of chapter 11 with this screencast. We will find out. Depends on how talkative I get along the way. In any case, we're asking the question, how does energy get from one place to another? And underneath that question, or subsidiary to that question, is how do we measure how fast that energy can get from one place to another, and what is the mechanism by which the energy gets from one place to another? We asked these same questions way back in chemistry. During a chemical reaction, we often wanted to know how fast does this chemical reaction take place, and what happens in order to get from reactants to products. In other words, what does that arrow represent when we say the reactants turn into products? The mechanism is represented by that arrow. It doesn't happen magically. It doesn't happen instantaneously as the particles moving around and collide with each other. We're going to realize that there are basically three mechanisms. And the first mechanism is talked about right here, which we'll get to in just a second. Earlier in the chapter, we defined heat as the transfer of energy between a system and its surroundings. And whether you're talking about chemistry or physics, it's always important to distinguish or discern what is the system and what are the surroundings. Is the energy or heat or whatever, or information or material going from the system to the surroundings, or is it going from the surroundings into the system? And this will dictate whether you have a positive or negative sign in that transfer. Well, we have three kinds of mechanisms that help us to understand how heat gets from one place to another. And the first one is called conduction. Now, the word conduction begins with a C, the word contact begins with a C, and the best way to remember what conduction is to think about the fact that all the particles that make up your system, as well as the surroundings, are moving around and colliding with each other, and when they collide with each other, they come into contact with each other. And so the energy of rapidly moving particles can be given to other particles that aren't moving as rapidly until you have a average kinetic energy for all the particles. Remember, temperature is a measure of the average kinetic energy of all the particles in the system. So thermal conduction, or just simply conduction, is going to be the way in which heat moves from one place to another by means of coming into contact. Both two materials being side by side. For example, the cold air on the outside in contact with your glass window, and your glass window being in contact with the air on the inside, but also the particles of air moving around and colliding with the particles that make up the glass, and which come in contact with the particles of the air inside the room. Later on in physics, we'll talk about conduction as a way in which electricity moves from one place to another through conductors. And we'll talk about what makes a good conductor of electricity and what makes a lousy conductor of electricity, just like we talk about what makes a good conductor of heat and a lousy conductor of heat. So you can expect the word insulation to come up pretty soon. So we're talking about the movement of particles. And I guess I would maybe add ions to this group of particles as well. Typically in chemistry, we think about molecules and atoms and ions as being the particles moving around. We include electrons here. And as you probably all know, as we get closer and closer to winter, of course that depends on when you're listening to this screencast, when we use a blanket, the blanket traps air, and so between the blanket, which is a relatively poor conductor of heat, and the air that is trapped within the fibers of the blanket, that's definitely a poor conductor of heat, it helps to trap your body's heat underneath the blanket. and therefore helps to keep you warm while you sleep at night. Now, coming down here to the bottom, the energy, therefore, is kinetic energy because the particles are moving, 1/2 mass velocity squared. And the faster the particle is moving, therefore, the more energy it's going to have. The closer together the particles are to each other, in other words, the denser the material, the more collisions you're going to have, which means the transfer of energy is going to be greater. The farther apart the particles are, the less rapidly heat is going to be transferred because you won't have quite as many collisions and so forth. Now, if we imagine this material over here in figure 11.5, and we have a temperature on one side and a temperature on the other side. Let's say that this temperature is the hotter temperature, this temperature is the cold temperature. And so the heat always goes from hot to cold. That seems to be a fundamental thermodynamic principle of the universe. The net flow of heat is always from hot to cold until you reach equilibrium. Eventually, sometimes you reach equilibrium very, very quickly. Sometimes you reach it very, very slowly. In the case of a star, which is generating its own heat and releasing that heat into space, it may take thousands and thousands of years before the star, eventually what's left of it, is in equilibrium temperature-wise with the space around it. And you can begin to see that whatever this material is, might be a material through which the heat can transfer very quickly and efficiently. In other words, it could be a good thermal conductor, or it might be a material that is very poor, that doesn't allow the heat to transfer very well, such as, and here's a listing of them: asbestos, cork, paper, fiberglass. Gases are very poor thermal conductors, and so forth. Metals are very good thermal conductors because of the ability of the electrons, which are very, very loosely held by the matrix of positive nuclei in the metal crystal. Because the atoms of metal are arranged in an orderly fashion, metals are crystalline, just like table salt is crystalline by that definition. And all the electrons are, the outer shell electrons, the valence electrons, are loosely held by the matrix of positive nuclei. And remember, we said those electrons are delocalized. And delocalized electrons, therefore, are why metals are good at conducting an electrical charge as well as conducting heat. They're not locked into their orbits. So you can also imagine that the bigger the temperature differential, the bigger your change in temperature between one side and the other side, the more rapidly your heat is going to be transferred. And if we were to come up with some kind of graph where we were talking about, let's say this is the change in the amount of the change in temperature, and this is the rate at which the heat is transferred. The rate is very, very great. If this is going to 0, and I'm making this up on the fly here, the rate is very, very great when the temperature is greatest, and then the rate slows down and gets less and less as the change in temperature from one side to the other gets smaller and smaller. Until eventually, when that change in temperature between one side and the other is 0, the rate goes to 0. That doesn't mean you don't have particles moving to the left and moving to the right. It's just that they neutralize each other. Other factors that would be involved, of course, would be the distance, not only through which the material has to go up here, this delta X, but in this case, if we have a hot temperature and a low temperature, the greater the distance from left to right, that's going to be a factor in heat transfer. And what that material is made out of is going to be a factor in heat transfer. So heat, of course, we can use the letter Q here. The amount of heat can be an mc delta T. It can also be a mass times the latent heat of either fusion or the latent heat of vaporization for when materials are changing state. But Q is going to be the amount of heat per time, and heat per time is going to be called energy per time, generically is power. And power is measured in watts, joules per second. Joules per second. So a joule second, if I measure, a watt second, if I take a watt of power times a second, in other words, if I multiply power times time, I get Q, which is joules. A joule is a watt second if we do a dimensional analysis. Now, moving on down then, this amount of heat that changes per time is going to be proportional, first of all, to the cross-sectional area. Is it a narrow wire, for example, that the heat's trying to get through? Is it a large, wide open space? But that cross-sectional area is proportional to the rate of heat transfer. It's also proportional to the change in temperature, and it's inversely proportional to the length through which the heat has to transfer. If you have a thin pane of glass versus a very, very thick pane of glass, the amount of heat that's going to get through is inversely proportional to the thickness of that glass. So all of these factors are involved. So when we put all of this information together, we come down here and we see that the power, that is to say the amount of heat that is transferred per time, the power, the watts. We have our proportionality constant, which is our thermal conductivity. We have our change in temperature. The bigger the change in temperature, the more rapidly heat is transferred. The bigger the cross-sectional area, the more heat will be transferred. And the greater the distance the heat has to travel, the less the heat will be transferred. So hopefully you see that this equation 11.7 makes a lot of sense. Let's take a quick look at some of these thermal conductivities over here on the left. And if you do a dimensional analysis and solve this equation for K, you would get these dimensions right here. And you can see that metals have high thermal conductivities, as you might expect. And if you remember that metals are much denser than gases because the atoms that make up a metal are 10 times closer together along the x-axis, 10 times along the y-axis, and 10 times closer together on the z-axis. 10 times 10 times 10 is about 1,000. And you can see that your gases are very roughly have a thermal conductivity about 1,000 times less than the metals do. Gases are about 1,000 times less in their thermal conductivity and their ability to conduct heat from one place to another. Non-metals would be non-conductors, and they are a little bit more than the gases, maybe by a factor of about 10 or so, roughly speaking. Again, this is a good place to pause and take your quick quiz and see how you're doing in terms of your understanding. This problem for the biology majors taking this course, or the people going into medicine. If a human being has a layer of fat and muscle that lies under your skin. Now, think about that statement. You know that varies greatly. Think about the top of your head has practically no fat or muscle at all, just some layers of skin. Maybe your shins, for example, other places where your bone is right next to your skin, like in the jaw. There's not going to be quite as much muscle and fat, obviously, as in other places, like in your stomach and chest and your gluteus maximus and places like that. So obviously this is going to be a ballpark estimate, whatever this problem is going to be. And it says here that in response to cold environment, and you've probably noticed this, sometimes we call this goosebumps, when the capillaries near the surface constrict, reduces blood flow. And of course, blood flow means that the blood, which is made up of blood cells, which would, in a sense, we could say are very, very large particles moving along carrying heat. And when you restrict the flow of blood, you restrict the flow of heat, leaving the tissues. And that helps to keep you warm. And they talk about the thermal conductivity, very, very roughly, when you average it across the body, as 0.21 watts per meter Kelvin. And then they have a very average thickness of 2 centimeters, which obviously is quite large for some places on your body and quite small for others. This would be a little bit lower than body temperature. Body temperature is usually about 37 Celsius. So this, being the skin on the surface, is not quite the same as your internal body temperature. And we have some problems to solve. So problem number 1, estimate the rate of loss. So we take the equation on the previous page that we just derived right here. And this is just basically plugging in the numbers from the problem that are given to you. And we get 73 watts, so that should not be a problem. I will point out something, though, that if you see a problem like this in your homework, chances are you're not going to have meters, particularly maybe in this one right here. Things might be in centimeters, for example, or millimeters, but make sure you have dimensional consistency, because if you're using watts, which are joules per second, you have to have your units of length have to be in meters. Now, your temperatures can be either Kelvin or Celsius, but not Fahrenheit, in order to be consistent as well. Part B, calculate the thermal energy lost due to conduction in 1 hour. Well, if we take our equation, power equals Q divided by the change in temperature and multiply by the change in temperature, we get Q, and we take our watts from the previous problem times the number of seconds in an hour, and that problem is pretty easy. And then when we come down to the bottom problem, letter C, estimate the change in body temperature in 1 hour. We remember this equation, Q equals mc delta T. We solve it for delta T, and we plug our numbers in. We already have our heat from part B, and here is our mass of the body. And this number, let's see, down here is your joules per kilogram Kelvin. And we get a change in temperature of 1 degree Celsius. All right, let's try to remember where this comes from. I'll leave that to you. All right, any ideas or remarks? And that is that this is a very, very rough estimate for a lot of reasons, one of which is there is also the transfer of heat out of your body from convection. Obviously, you're breathing warm air out. You're radiating heat outward. We'll talk more about convection and radiation in just a few minutes. And then a big one is any perspiration on your surface of your skin as it evaporates. As the water goes into the vapor state, those molecules of water in the liquid state need energy to go in the vapor state, so they take that energy from your body, which cools you down, which is nice in the wintertime, but if you don't need to be getting any colder, then of course it can be very, very dangerous. All right. Let's come over here. Practical for engineers and builders and civil engineering, home insulation. Not so much anymore, but a number of years ago, most of the time we talked about British thermal units as our measurement of heat, and British thermal unit is very different from a calorie, which is different from a joule. A calorie is the amount of heat it takes to raise 1 gram of water 1 degree Celsius. A British thermal unit is the amount of heat it takes to raise the temperature of 1 pound of water 1 degree Fahrenheit. And so you could buy appliances, for example, stoves that were ranked at so many BTUs, or toasters or furnaces. You could buy air conditioners or refrigerators, and they would tell you the BTUs of heat being able to be removed. You don't see BTUs quite as much anymore. In any case, we've had this already in the chapter a couple of times in this very screencast. But what we're doing right now is we're recognizing that getting in the way, therefore it's in the denominator, getting in the way of this transfer of heat, which is going to be joules per second, or watts, are going to be these barriers to the flow of heat. We call them insulators, or insulation. And many times you have multiple things. For example, if you think of one of the vertical walls in your house, the exterior wall, maybe you have bricks on the outside, and then the bricks are put over some type of fibrous material that you can sometimes see. That's a vapor, not a vapor barrier. That would be another material, sort of a plastic coating. I mean, like a plastic sheeting, and then that might be over a fibrous material. And then that's going to be maybe over some fiberglass like this right there. And then on the other side of the fiberglass, you might have your drywall on the inside of the house. And then on the inside, over the drywall, you might have a couple layers of paint. Or maybe you have some paneling. In any case, you can have multiple things between the inside and the outside of your house. And so we're going to have the summation of all of those insulators. And an insulator has a certain thickness, and it's also going to have a value K. And you remember what K is from back here, the thermal conductivity. If you can follow along as I move the screen all over the place. So we call this L divided by K my R value. And when you go to the hardware store, for example, to buy something for insulation, you always are interested in its R value. And the R value is usually given in terms of its thickness. So, for example, fiberglass, the R value would depend upon how thick the fiberglass batting is. You can have different thicknesses of glass. You can have different thicknesses of drywall. So, and all of these kinds of things, therefore, would affect what its R value would be. Now you can see we like to use fiberglass, especially in exterior walls and underneath the roof, because they have very, very large R values, and therefore they block the flow of heat very, very effectively. The other things have lesser values of heat. It's also important to recognize that the surfaces of your walls are not perfectly smooth, even though they may seem to be. And so there's always this thin layer of stagnant air on either side of the wall, which, to be really careful when you calculate your overall R value, you need to include in your calculations. And so we add all of these R values up when we do a problem, when we're trying to calculate the ability of some insulating materials to impede the flow of heat from one place to another. So if we take a look at this problem right here, calculate the R value of several layers of insulating material. And so you can see we've got concrete, we've got drywall, we've got fiberglass batting, We're even going to have perhaps some of that stagnant air on either side. And so let's take a look at the problem quickly. Find the energy transferred in 1 hour by conduction through a concrete wall. So what we're going to do is first of all calculate our R value. And our value, therefore, is going to require us to add up two things. The R value of the concrete and the minor adjustment we have to make for the stagnant air on each side of the concrete wall. And we're going to add those together. And therefore we get the equation to the right. And when we do our calculation, we get our value of R of being 0.31. Now we can then take our thermal conduction equation, which is right here. And now we can plug our numbers in. We have our cross-sectional area. We have our change in temperature differential. Here's my value of R. That goes in the denominator. And we get 353 watts. You'll notice we have 2 sig digs right there. We have 2 sig digs right there. So therefore, we round our answer off to 2 sig digs. And that little lesson there is for all of you sig dig deniers on your homework. You know who you are. Then we can convert this into joules by taking our wattage and multiplying by the number of seconds in an hour to get our number of joules in 2 sig digs. Now, if I were doing this problem, I would keep my extra significant digit from the previous problem, but then round off at the end. Just a little bit more precision in the final answer. Calculate the R value of the newly insulated wall. And so we're going to add up the outside air layer, the concrete, the sheath, the fiberglass, the drywall, the inside air layer. I'm going to add all of them up. Again, those air layers are important but pretty small components. Nevertheless, we add them all up and we get the value of 2.5. Now look at the units. You might say, and this is in the blue boxes, the units up here, you'll notice that in the denominator, you have, actually in the denominator of the denominator, you have seconds times degrees Celsius. And anytime you have something that's in the denominator of the denominator, it ends up in the numerator. So these units in the blue circles are identical. Pay attention to dimensions or you will suffer from dementia. All right, calculate the energy transferred. So here's our thermal conduction equation again, and now we're just plugging our numbers in. We take our answer from part B and put it down there. And we can find the amount of heat is 44 watts. And then finally, using our thermal conduction equation again, we can calculate our overall change in temperature by solving for delta T. All right, the second way in which heat goes from one place to another is by way of convection. And the key word to remember or associate with the word convection is the word current. Current is going to be the movement of a fluid. We're not talking about electrical current here. We're talking about like the current in a river. In fact, one of Missouri's rivers is named the Current River. But we're talking about the flow of a fluid. And it can be air or some other gas. It can also be a liquid, the flow of a fluid. This is convection. And this is how heat can get from one place to another. Right off the bat, you should recognize that convection does not take place in outer space. The heat that comes from a star, such as our sun, does not have any material that can flow from the sun to our earth. So convection is not a factor in how we get our heat from the sun. And of course, outer space has practically no particles, maybe 1 particle per cubic centimeter, which really isn't dense enough for conduction to be a factor in the way in which heat is transferred from the sun to our planet. Therefore, there must be a third mechanism, and of course, we're going to get to radiation in a little bit. So, as the density of air increases, goes down, the air is going to rise because less dense things float or rise above denser things. And the transfer of energy by movement of a substance is called convection, so heat rises. Over here, you put your hand not in the flame. Please don't do that. Put it above the flame, and you can feel the heat because of this heat current, this current of air as it rises. And of course, as it rises, it begins to spread out as well. This is natural convection, but you can also use a fan or a pump. When your furnace fan kicks on in the wintertime, it pushes the air from the furnace where combustion is going on with your natural gas, likely, and it's pushing that air to all parts of your house, warming your house up. That would be convection. Some other examples would be a tea kettle. The base of the tea kettle is on the stovetop. That's the water that heats up fastest. As that hot water heats up and the water molecules move faster and faster, they spread out. As a result, they get lower in density. Because they're lower in density, they begin to rise to the top. As they rise to the top, the cooler water at the top, which is denser, begins to sink and come down and then get heated until pretty soon all the water in the tea kettle reaches the same temperature, and then you begin the boiling process. Well, we can say the same thing for a radiator. Whether it's one of those old-fashioned metal radiators that old houses would have, like 100 years ago, and you can even buy radiators because some people like the heat that comes from hot water radiators, and these newer radiators are much more efficient than the old-fashioned ones, and are usually heated by electricity because you plug it in as opposed to from hot water coming from some place where the water is boiling, because that requires additional plumbing. But the radiator that's along the floor, as the hot air around that radiator warms up, its density gets lower, and I drew that arrow backwards. The density is going to go down, and therefore the warm air is going to rise, because if it's less dense, it begins to rise, so it floats on the colder air. And the colder air, which is denser, it's got a bigger denser, it's going to sink so that it can be heated up as well. In an automobile engine, of course, we rely on the cooler water to circulate through the engine and pick up heat, and then that heat being carried away so that the engine doesn't overheat. Of course, in a car engine, there's also a lot of heat that is carried away by conduction, because the hot metal pipes and the hot metal pieces of the engine are in contact with the water and transfer water by means of conduction. And this fan, the water is pumped. You have a water pump that forces the cold water to pick up the heat, then it forces the now hot water to move in front of the radiator, where it can be cooled down again as the car is moving, and where the fan is blowing. Of course, if your water pump goes bad, then the water is not going to get circulated, and then your engine can overheat. And everybody, as sooner or later, somewhere around, I'm just guessing here, about 100,000 miles, or sometimes earlier, sometimes later, depending on the age and quality of the car, the water pump is going to have to be replaced. Another important vocabulary term is the idea of a temperature gradient. A temperature gradient depends upon the difference in temperature from start to finish. And the greater that difference in temperature, the greater the temperature gradient. Heat moves much faster when the temperature gradient is greater, and heat hardly moves at all when the temperature gradient is very, very little. And if you think about a body of water, and this has got to be deep enough that you can dive into and go 10, 20 feet down into the water or more. And the water that's nearest the surface is going to be in contact with the air. It's also going to be picking up radiant heat from the sun. And so it's going to be the warmest. It's going to be pretty close to the temperature of the air, or at least warmer than any other part. But then as you go deeper and deeper in the water, it gets cooler and cooler. And at some point, you reach this level right here at the bottom of the thermocline. And even on a hot July day, you get down to that depth, which might be 20 feet down, too deep for the radiant heat from the sun to penetrate very well. And you actually would need a wetsuit to be down here at this cold temperature. You would get hypothermia quickly. The one time that I had a wetsuit on and went scuba diving with some used equipment that my brother picked up out of the tailgate of some guy leaving college, and he didn't have room for it, which was pretty risky on his part and risky on my part. And then he gives me a 15-minute lesson on how to use the scuba diving equipment. But when we went down this is Table Rock, I believe, on a hot July day, it was probably in the upper 90s in the air. And then we got down here, and we were glad that we had the the insulated isoprene wetsuit on as we were down here. Now, the water was so murky, you really couldn't see anything, so it wasn't the most pleasant or interesting of experiences. But I did it, and I survived, which is saying something, because my brother is much more of a risk taker than me. He's come closer to death way more times than I have in some of his wild excursions. He lives out in Idaho, so he's that kind of person. I love him. All right. Anyway, so as the seasons change, as you go from summer to fall, and the air begins to get colder and colder and colder, it turns out that the air at the surface now becomes the coldest air. And the air at the bottom, which has been insulated from the cold, is warmer. The cold air sinks because it's denser, and the air at the bottom then rises to the surface. And this happens when you, over the fall and over the spring, as you go through your big temperature changes between winter and summer, and then summer to winter. And this sort of helps to keep the circulation going in the water, and it also brings up nutrients and stuff like that at the bottom towards the surface, which can have both a good and a bad effect. Because you don't want to get an algae bloom, which can happen when you have too much fertilizer in the water, and it causes the algae in the water to grow in too great of an abundance. All right, little applications up here. We as human beings have some layer of fat, muscle, skin to help conserve our body temperature. Some of us, we always are monitoring this level of fat, but it's important to have some. Birds ruffle their feathers. If you see a robin in a cold winter day that looks really, really plump, it's ruffled its feathers, trapping air, insulating it. Animals can bristle the fur, again trapping air. And of course, we can't do either of those things. In case you haven't noticed, we do not have fur or feathers, though I've seen some guys with pretty hairy bodies. But nonetheless, that's why we wear sweaters and, of course, a down jacket. The goose feathers that make up the down, or the artificial fibers that make up the down, trap the air and help to keep us warm. All right, method number 3. Heat can get from one place to another through radiation. And if you were to put your hands on the left side and on the right side of a candle flame, you can feel its heat. Or shine a light off to the side. There will be some heat that's going to rise, convection, but you'll feel the heat off to the side, and that's radiation. And most of that radiation is in the form of infrared. Infrared is part of the electromagnetic spectrum, if you remember. And it's just a little bit beyond the red and the visible red. It has that slightly bigger wavelength, so that slightly smaller frequency. So the photons of infrared have less energy, of course, than the photons of ultraviolet. Now, the Stefan's law, when we talk about this law, which is over 100 years old, it comes from a Austrian guy, Joseph Stefan, and from 1835 to 1893. He was a physicist. Oftentimes in some of the writings, he indicated a personal faith. He often talked about relying on God in his personal reflections. He went through some difficult times in his life where he expressed that more than at other times. But like many scientists, they're often very quiet about their faith. Either they have a significant Christian faith, or maybe they have a faith in some other religion and they just don't talk about it. But that is all of us are very, very different, and to the degree in which we talk about what we believe outside of our the kind of work that we do that maybe most people identify us with what we do. Hopefully, those of you who are Christians, you will be identified both by the excellence of your work, by the excellence of your character, but also by the kinds of things that you say and write about, besides the technical things that you say and write. I think St. Francis of Assisi is said, or at least this is attributed to him, he says, share the gospel. If necessary, use words. All right, Stefan's law is right here, and it should be pretty logical. The rate in which heat is going to be transferred via radiation is going to depend upon the cross-sectional area, just like through conduction and convection, the cross-sectional area of the material through which the heat is being transferred. It's also going to depend upon the temperature. So hot things are going to radiate heat way, way more than cold things. It's not often you see an exponent of 4. Sometimes you see it in 3, certainly with volume, for example. And then we've got these two unusual constants called the Stefan-Boltzmann, or SB constant, represented by lowercase sigma, right there. And we also have this emissivity, which is a property of the material through which the heat is radiating, given by that script lowercase e. And the lowercase e can have a value between 0 and 1. And it's called the emissivity constant. So what do we mean by the word emissivity? Easy for me to say. Emissivity. Now, the key here is not to think of emissivity as being a ratio of energy coming in versus energy coming out in the transfer process. But think of it as a subtraction of energy coming in, right here, and then energy that is reflected. So if you have a substance, and you can think like, let's say we have a basketball sitting outside on the lawn. You can talk about the amount of heat radiating that from the sun that is entering the basketball. And then you can also talk about the amount of heat that is radiating from the basketball. And if you were to measure that off of a particular portion of the basketball surface, you could calculate the value of E, the emissivity constant. So when emissivity is 0, that means it's very, very, very shiny, like something that is steel or some other metal or a mirror. It's reflecting all the heat that's coming in. So all the heat coming in minus the heat that's reflected gives you 0. So an emissivity of 0 means it's not absorbing any heat at all. And of course, objects can approach 0 emissivity. Now, an emissivity of 1 means that all the heat that's coming in is being absorbed, and the amount of heat that is being reflected this amount of heat is 0. So if all the heat coming in minus 0 heat being reflected, we give that a value of 1. And that's called a black body. A black body absorbs all the heat. And if it absorbs all the heat, that of course means that it's going to appear to be black because there is no heat being given off in any of the wavelengths, so you can't see it. But we got to qualify that, and this is going to sound really weird. And that is that the sun is considered a black body. And the reason the sun is considered a black body is because any heat from the outside that shines onto the sun is all going to be absorbed. But the sun is producing a lot of heat, but that's the heat being produced on its own because of fusion. It's a star after all. So it's interesting to think that something that is blindingly bright is actually considered to be a black body. Your skin, by the way, has a emissivity of close to 1, so it absorbs an awful lot of heat and doesn't reflect much. Let's see. A black hole, of course, would have would be a black body. And we come over here, and here's our equation for finding the change in the amount of heat. And there's my Stefan Boltzmann constant, which is a given. There's my emissivity, which I can look up on a chart. This is the cross-sectional area through which the heat is going. And then again, you've got these two values to the 4th power. You'll probably have to look at, practice around and play around with your calculator to learn how to do powers to the 4th again. So an ideal absorber is going to absorb 100% of the heat. It's going to be called a black body object. And it mentions here, of course, that the sun, even though it's bright, is considered a black body. An ideal reflector, like a very, very shiny surface of metal, is going to approach 0 and have an emissivity of 0. One of the reasons we wear white clothing in the summertime is because it reflects an awful lot of light. And so it's going to be cooler to wear. And in the wintertime, we wear dark colored clothes because they do absorb more of the heat to help to keep us warm. We have ways of taking pictures of this thermal or infrared heat called thermography, and various ways to do this. Sometimes we use computer software to help enhance the very, very minimal amount of heat that can be detected. Or maybe we measure the infrared, which is invisible directly, and then the computer puts it into the color region for us so we can see it. You can see in this picture of this house that the blue area at the top means that very, very little heat is being radiated out. And the red area and the white would be where lots of heat is escaping, as you might expect, through the windows. So the owners of this house would benefit from getting some better windows that can block the flow of heat. Modern thermal panes would have multiple layers of glass, and often they inside between the layers of glass they put argon gas so that you don't have zero pressure inside, and this really retards the flow of heat. I remember this is a couple decades ago, they used infrared cameras from a helicopter flying over a neighborhood because there was a particular house, I think it was in South County, that had a huge electric bill. And the people in this house were already suspected of growing marijuana in their basement. And so they had heat lamps in their basement using electricity. And sure enough, this house lit up like a torch with infrared photography. Here is a picture of a woman who tragically has breast cancer. And you can see that the cancer, of course, is going to be rapidly dividing cells, going through that mitosis process where they never specialize. The cells never go into the part of their cell cycle where they do the function that they're supposed to do. They just keep dividing and dividing and dividing, forming a tumor of significant mass. And that, of course, releases heat, which can be detected. And here's another way of looking for this infrared heat, this radiated heat coming off the eardrum. And the eardrum is very close to the hypothalamus, which happens to be the body's temperature control system. It's a lot better than trying to stick a thermometer into a child through one of two uncomfortable openings, depending upon how you go about it. Thermal radiation and night vision. This math is not terribly difficult. I'm going to just touch on it quickly. You will always be given the instructions about how to convert Fahrenheit into Celsius if necessary, but you should all know that in order to convert Celsius into Kelvin, you add 273.15 if you need extra sig digs. You need to have the temperature in Kelvin. Notice we do not talk about degrees Kelvin. Kelvin, it's just a straight Kelvin, not degrees Celsius. Well, we do have degrees Celsius, but we just talk about kelvins. And then once we have our temperatures, we can plug them into right here. There's my constant. We look up the emissivity constant. There's my cross-sectional area, which might not be given to you in meters squared. Make sure you pay attention to dimensions. And we get the power, and like before, we convert the power into joules. And coming over here, we can also try to find the power output of Alpha Centauri. This is in a star cluster that is one of the nearest star clusters to planet Earth. And we can also calculate what power is intercepted by another planet that might be in the way, let's say Alpha Centauri b with a certain radius. And the math, again, is pretty straightforward. The surface area of a sphere is 4 pi r squared. And once we calculate that surface area, then we can take our Stefan's equation right here and plug our numbers in and get our watts. And that's a significant amount of watts because, of course, we're talking about a star. And then down here, we can compare the surface area of our star to the surface area of the object that's eclipsing the star, the planet, and find our ratio by plugging these numbers into the ratio. And we get the fraction of my power that's actually striking the planet's disk. And therefore we can find its wattage, and you can see we're down to 10 to the minus 19th when the star's output was 10 to the 26th. So we're down by a factor of 10 million already. And then we can plug it into Stefan's equation in order to calculate the actual temperature. And we get a temperature of 1,880 degrees Fahrenheit, just so you have a benchmark there. The last thing on this screencast, which has gotten pretty long, is the Dewar flask, also called a thermos bottle, capital T, because that's a company name for the thermos bottle. When I was in grade school, I'd carried a lunchbox in my school. Some of my classmates had government provided beverages because of their income, and my family was just above that level, so I had to bring my drink in a thermos. And this is my thermos, and I frequently broke these things because they were glass, but it kept we didn't have any refrigerators in our school, and so this kept my drink cold. I think it was milk. And on special occasions, we might splurge and we might have chocolate milk, and that was a big deal. In any case, there's the Dewar flask can keep things very, very cold for long periods of time because it deals with all three. It deals with conduction, convection, radiation. Obviously, inside the flask, you're not going to have any currents going on, so there's no convection. As far as conduction is concerned, you're going to have sort of an insulating material between the outside here and the fluid that's on the inside, non-conducting material. So that reduces conduction big time. And because it's silvered on the inside, very shiny on the inside, it radiates whatever heat the material has back. So whatever heat comes in is going to be radiated back. And you see these often when you're working in low temperature physics in cryogenics, where you're storing liquid nitrogen. You go to the dermatologist and they might use liquid nitrogen to burn off a mole or a basal cell carcinoma. I just observed that being done to my dad, unfortunately. But basal cells are not as bad, obviously, as melanomas. So in dermatology, they might use liquid nitrogen. Physics demos, we use liquid nitrogen, especially when we're trying to show superconductivity. And then when you have instrumentation in outer space, you got this rather remarkable situation that if you have a satellite that is going in orbit, some of the orbit is, as you go around the Earth, is going to be during the daytime, you get intense radiation from the sun, and then at nighttime, it's extremely cold because there is practically no heat at all. So when you go back and forth between super hot and super cold, instrumentation, especially sensitive computerized instrumentation, doesn't fare very well. So by putting them into a flask like this, it insulates them from the extremes. And we will stop there.